So, welcome to my talk, everybody. Hello. This is Binary Golfing UEFI application. So, let's do a quick rundown. Who am I? I'm Netspooky, I'm a security researcher. I'm founder of the Binary Golf Grand Prix, and I've been involved in other community projects as well. So, here's what we're going to talk about today. This is the talk outline. So, we're going to go over basically the whole thing, because there's kind of a lot to explain here. Not just the UEFI and firmware, but like why the heck we're even doing binary golf in the first place, like what it is. So I'm going to give you the context for that. Then we're going to talk about UEFI itself, just what it is, get everybody on the same page. We'll talk about writing UEFI applications, learning the ABI, and then implementing self-replication and assembly, learning about the parser and kernels of how applications are actually loaded. And then we'll talk about making the binary very, very small. And if we're lucky, we'll get to practical applications of what to do with tiny binaries. So let's go over the background real quick. So first, before we even get started with anything, because I get this question all the time, it's like, why actually golf the UEFI app? So in late 2022, I was working on several projects at once, and I was studying a lot of firmware, boot ROM, and bootloader stages, parsers for different files. A lot of them are ELFs, some of them are custom formats, but I was interested in UEFI because they're another type of firmware that people use. People use them all over, all the places on this computer right now. And I wanted to understand how that handled binaries as well, because they're usually pretty jank. They kind of only do what they need to do because they fit the code in like a, their SOC and stuff. So I wanted to understand that. And I also wanted to create a little payload that I could drop. We're gonna do a little boot kit, but I ended up moving it to BGGP entry, but I did a paper with my friend RQU on how to make very, very tiny Linux kernel modules for temp out volume 3. So what is binary golf? So you may have heard of code golf, which is like making code that does something in very few lines of code or characters. This one is more broad in that it covers file form, the whole file format itself, right? So there's, you may have heard of the polyglot file and things like that. So pulling all these things together from code golf, demo scheme, size coding, making very tiny assembly tricks and things like that. Also the virus writing itself, polyglots, and exploit development, all this fun stuff. You kind of pull it all together into the field that we're now calling binary golf. So the core aspect of binary golf is that constraints will lead to creativity. Same thing with pixel art, same thing with 8-bit music. Like you have to kind of use the platform and the constraints that you have, and it forces you to do things. And it's hard because nowadays you can go on like AWS and just one-click deploy like a whole web app and the whole infrastructure. You don't really have to think about like resource costs or how it actually works. And I think it's helpful to try to expose the underlying layers of technology to really feel and understand how things work. So the goal is to really get a meta understanding of the file format and the platform. And also you do get to find a lot of cool bugs in this, which we'll get into. So I did a talk about this before. This is my first talk about BGGP itself, because I did a talk at a virtual conference called AirGap 2020 before BGGP was even started. And so I had an early talk about my old adventures in that with a lot of ELF and other file format shrinking. But a lot of the inspiration for interesting files definitely comes from PRC or GTFO. So if you've ever seen Angel Bertini or anybody else working there, that's a big inspiration to this whole field. So what is the Binary Golf Grand Prix? So this is a yearly contest to create the smallest files that do something in particular. It started out as a joke. It's something that we didn't think would even happen, but people actually liked it, so we had to turn it into something real. So the very first one was to create a binary palindrome, which is a binary that executed the same backwards as it did forwards, but it also had to execute in the second half of the binary, so you couldn't just invert a binary, tack it to the end. So it was a lot of interesting tricks there. We got some like demo scene people coming out of the woodwork for that. It's really cool. Then we did smallest polyglot files, the crash one, which was one of my favorite ones, where we just found a bunch of bugs and we gave people points for patching the code, the bugs that they found. Last year's was replicate, which was the smallest self-replicating file. And then this year, right now, we have the download challenge, which is currently going until September 6th. And so the whole thing runs for the entire summer because we kind of want to give people enough time to do the things they want to do. You might need to take a month off and ponder and then come back to the challenge. So we try to make it really easy for people. I'm really into more chill CPS, although I love stuff like Flare on gives you like 6 weeks, which I think is really cool because trying to do everything in like one weekend, it just, if you don't have the time that weekend, you're not in the mood, it kind of sucks. So, but if you want to know more, binary.golf is the website, all of our challenges, the entries, everything's on GitHub, and you can see everything you have. So here's a slide, which is our greatest hits, I think, of BGGP. We found a lot of interesting things here. There's polyglots. Friend Harvey found a remote code execution on the cell modem in a Game Boy, which we were able to do. It's got a bunch of coverage. One of our volunteers here, Davey, found got the first CVE for Flipper Zero with the NFC loader bug. There's tons of things in here that I'm really proud of that people have done. So this is kind of like an example of the work that people put together. We want everybody to bring their best. So BGP4, the challenge was to replicate. All you had to do was to self-replicate your file and print the number 4. It could be any file format you wanted, any platform, any architecture, whatever. All you had to do was those 2 things. So this is the flyer and that's the challenge page. Okay, so now we get into what is UEFI. So I'm gonna go over this kind of quick because you don't have to get into all the internal stuff. UEFI is a unified firmware interface, and the goal of it is to make a firmware layer that's easy for people to interact with in code in place of a traditional bootloader. And it also allows the operating system to have an easy way to interact with the firmware layer. And so if anybody has ever programmed with BIOS, you might know that it sucks and it is awful and it's painstaking. If you ever tried to make a bootkit in old school BIOS, you know it's very, very painful to do with CHS and all their stupid platform initialization things. So these UEFI tries to answer that question of how to actually do this in a more sane way by kind of compiling everything that you want and making it repeatable across different architectures and platforms. And also, yeah, shout out to Ralph Brown. That list is getting very big still. So yeah, UEFI basically makes it easier for people who want to program stuff. They have this driver execution environment. Everything kind of runs in, and you have a way of interacting with certain peripherals and things that are in a standard format, so you can easily port your code. And you can use drivers and applications to set up and do things up in UEFI. There's a lot of features. There's a lot of cool tables that have all the platform info. There's good APIs, file system access, which is amazing because I hate disk geometry and network access, things like that. And it lets you just kind of make applications that are easy portable. And there's also an IRC client. I don't know if anyone's tried, but it's a very cool concept to just come through on UEFI. So how does it boot in OS? There's a lot of things. I'm not going to get into all the internals of how it boots. This is more about the parser itself. It sets up, does a bunch of stages to load things, and it's all defined, and there's a specific way that you do this. And so it sets up everything for you, gets sort of queue services, boots the OS. You're in the runtime environment. OS is running other drivers, and that kind of thing. So let's talk about how to write from UEFI applications real quick. I need some water to this laptop. I have quite a deep voice right now from this party. So yeah, talking a lot. Yeah, so that's good. So UEFI applications tend to be things like a shell application, maybe like a Flash util, some diagnostic or helper thing. Drivers are things that actually stay running. So like when you have the OS booted, that is what you interact with as a driver, the runtime driver. So BGP4, I thought the application would be easier because you can actually see the result of the UEFI shell versus trying to figure out some other way to output machine code. So I stuck with UEFI applications because they're just easy to play with. So there's a few ways to do it, to write them. The most popular way is EDK2, but it has a lot of stuff on it I'll get into why I didn't really like it, but it's very fully featured, there's a lot of docs. There's also the UEFI, which is the new version of UEFI, which is a very bare bones implementation, but it doesn't have as many features, but it's easier to understand in my perspective. And then also, yes, you can of course write in assembly. And yeah, I was going to try to do a prop chain in the UEFI loader, but it just was not the address sizes were going to be too big, and it would just make everything very annoying to deal with, but it's possible too. So UEFI is what I use because when I look at the EDK2 docs, there's like too many different documentation, like entry points to go into. And so I kind of wanted something that was easier with the hacker version, basically. So yeah, it's hard because there's a lot of abstractions because there are things that are global. There's a lot of like implied things that you can use within UEFI, but EDK2 kind of makes it easier for firmware developers, which is cool, but it doesn't make it easy to understand exactly what's happening with all the graphics and stuff. And UEFI has some of their own things as well, but it's at least easier to follow. So this is how you write a basic UEFI application. I went on OSDev, shout out OSDev, and got the UEFI variables tutorial. So it's basically the same as any other C program. It's just got that UEFI main, and there's just very basic C program. But you have these two arguments, the UEFI handle and the UEFI system table come in kind of like the R C program. And yes, your boy just wanted to go free. So you might have noticed in here too, there's a bunch of statements, there's print statements, and then there's also a UEFI call wrapper, so we're gonna look at here. But the print is one example of the wrapper that's talking about. So UEFI uses the UEFI call wrapper. It makes it easier for us to see how these calls are actually done because they set up all the arguments and just wrap them into a function. So the first argument here for this is output string, which is stored in the system table, P table, con out, which is the console output, and then output string is the function on that. There's two arguments in there, so if you put two, first argument is going to be the console output, and then the UTF-16 characters are in front. And so all this stuff is just basically in a bunch of trampolines that look like this. If you read the code, it's just there's a lot of swears in this code too, if you look at it, of how to get all of the function calls to work properly. But UEFI call wrapper is really simple to work with, so that's what I was trying to get as the bare way to understand how to make a real call. So this is the prototype for output string, and it has the arguments we saw in the code, which is the console output. There's a lot of types in UEFI, and they don't always make the most sense. They don't give you like the best name, but first one for this output protocol is just where we're going to output to, and then the string we're going to output. So now we know that there's two arguments we have to do to output string, which will help us solve the first part of the challenge to print 4. We need to kind of understand how UEFI expects us to give this data and make the call. So this is about the UEFI ABI and what the program sees when it starts. So you might be asking, how do you run UEFI? So the UEFI shell, which is here in this elevator, you can see is what you can use to run an application. And so we're going to be using OVMF, which is OpenVM firmware. It's provided by Tianocore, and it has the UEFI shell, which is their implementation of it. And we're going to be targeting x86. So to start a UEFI app, you just basically type the name of the shell, and all the applications will call the same functions that are available on every platform that implements UEFI, and you use the ABI to transmit your calls. So what does this actually define? So the ABI defines things like the calling conventions, like which registers you actually need to put values in to make a call, what the handoff state is, which is just at the entry point, what information is given to you, all the alignment requirements, and then anything else you need to know for executing code. So if you're used to programming in C, the compiler usually does all this for you. So basically the thing that separates is you have to just look up in the docs or reverse engineer a binary to figure out how to do this. So when the program starts, we talk about the entry point UEFI main. There you have the image handle, which is the handle that references the current images passed in RCX. And the system table, which is what we care about to call other functions, is passed in RDX. So this is the system table. It's basically everything that you're going to need to access UEFI features, all the pointers to boot services, runtime services, console, and then all the tables and stuff are stored and pointed to here. So most of the functionality that you'll see in UEFI is going to be referenced to with the boot services functions, with runtime services functions. And it's basically, it's given to you, so all you need to do is traverse all of those. And so there's really good documentation for UEFI, and I'm really grateful for it, because otherwise I don't know how I would do this. But being able to just read through and grab for all the stuff that you need is really cool, because we know how to set up call the UEFI call wrapper, so all we need to know is just what functions are even available, and then we can use them to write either C or assembly. And it definitely reminds me of writing the Linux programming assembly, because as long as you know how to column conventions and things like that, you can just use the man page or syscalls and just make your own programs. So yeah, talk about writing these applications in assembly. So people might ask too, why assembly? There's other valid ways to do this challenge. You could use a packer. You could do a lot of compiler tricks to make the binary really small. You could ask ChatGPT, although I don't know if it'll actually give you a real answer, but basically for me, writing an assembly gives you a chance to do unexpected and unconventional things in your code. Gives you a lot more, it's the same thing as the constraint aspect too, where you have to kind of think more creatively. But it also ultimately gives you a better understanding of how the actual program is supposed to work in the environment. And so it's a useful exercise if you haven't written any kind of programming system before. And this is a code that just, this is where tiny elf that shuts down stuff. These are great VTSs. All right, so here's our game plan of what we're going to do right now. So we're going to write a basic application based on the existing app that we have. Then we're going to sketch out the behavior that we want to actually implement, figure out how to actually call it, might look at some binaries in this assembler, and cross-reference stuff, test it in GDB, and then the last step is to optimize it. So you don't want to do it too early, because then it'll just be very annoying to debug. So first step is print forward assemblies. If you know how to do this already, because you know how to call output string, so we can translate that code, this C code, to assembly based on our column convention. So this is what it looks like. Very basic. You dereference the image handle in the system table. Okay, you set up your string and just do the call the way you know, based on the type and stuff. So pretty straightforward. Yeah. Does it work? Yes, it does. Prints 4. As you can see on the bottom corner there. And also debugging is actually really cool with QEMU, because you can use the -s flag and it'll open a GDB server for you, and then you can just connect to GDB when it's running OBMF. And you can debug OBMF itself as well as your UEFI app. It's kind of sharing the same address space. But it's pretty simple. You just add a -s to it and then just connect to it with GDB, and it's pretty sick. All right, so how do you self-replicate a file normally? So we know how to print 4, so we're going to do self-rep. Basically, the things we need to do are open the original file, open a new file, write the contents, and then close both the files. Right? So sounds simple enough, but every platform is different and has their own quirks, so we'll see. Did I? Okay. All right, so before I do anything, I've talked about UEFI protocols real quick. So UEFI protocols are basically just a collection of like functions and data that you can do to act on a specific device or a handle or something. They're referenced to GUID, and you can access them in a bunch of different ways. 2 functions that I've mainly used, like locate protocol, which just finds the first handle in the handle database that has the GUID that you're looking for. There's also a handle protocol, which queries the handle to see if it actually supports it. And every device has their own handle and their own protocols, and it's just handle the protocol all the way down. And you can also install your own custom one, which is pretty fun. So we have to write files. So we have to know how UEFI file system access actually works. And so you can access the same file systems as the OS and reference them from the disk. And you can just act on them, which is really awesome. I can't stress it enough how difficult it is to access files from a BIOS level and reload it. It's terrible. And so I looked at some examples of code to see how to actually do the opening of files and things like that. And so, yes, Swarm is system table connected. So this example is using locate protocol, which I mentioned before, and it gets the first handle that supports the simple file system protocol, which you use to get access to the open volume function, which can open a disk. So this is some code that I found on GitHub. Very nice reference. So once you get the file system handle, you can do the same process and iterate, just get the protocols you need from that handle to do the next step. And so really annoying part about this though is you have to include the GUID to do the lookups because that's how it works. And you have basically this high entropy string and you need to just keep it in your code, which is kind of annoying from a golfing perspective, but we'll get to that in a bit. So step one for this is opening the original file. Once you get all the handles to the disk, volume, all those things, you can open a file using the open function. It's pretty straightforward to use for just opening. It's kind of like an opening function on another system. And since we don't, this file already exists, we don't need the attributes argument, which is important for it. So if you open a new file, the new thing you have to do, which is to include the attributes flags for the file. And this is the 5th argument, which you need to put on the stack. And it has to be aligned with 20 bytes. And not doing this kind of messes everything up, and it's not easy to debug. So and I'll talk about this in a second. So to do the next step of like actually reading the file and stuff is you have to allocate memory first. You use allocate pool, and then you read the original file from the handle into the memory area, and that's pretty much how you get the contents of the file. And I also had an issue because this buffer size is both an in and out, as you can see. I just overlooked it, but I thought it was a straight up int, but it was actually a pointer, and that also messed things up, which caused a lot of damage. So yeah, after you get the memory area full of the original file, you can use the write function and write to the original or the new file, and then that's pretty much it. You can also get away with not closing the original file, but you can't with the new file because you have to close it to actually write it. And so, go to my real challenges here. So, I had a lot of problems with this, right? And I started, because I was writing in assembly and not writing in C because I gave up on the build system that I had. I was writing this in assembly a bunch, and I didn't do things like aligning the stack properly. The buffer size thing that I talked about wasn't a pointer, it was an int. And also, because of that, it was writing like the address of like early on at the beginning of memory. So it was just a lot of horrible things were happening. But because of this, I ended up like actually refactoring the code and making it better. So that was helpful, but it came at a great cost. And also big shout out to Ice Queen. I asked her, like, what am I doing wrong? She was like, oh, you have to align the stack at 20 bytes. Like, okay. But I was pulling my hair out for a while. And yeah, this is what it looked like too when I was dumping the actual data. It said AF. I was like, that's not my file. I don't know where that even came from. It's crazy, but yeah. All right, so here's a summary of the calls you have to do in case you want to reference them. You kind of went through them fast, but it's mostly, I don't want to be programming much here. But I got the output string for the printed for, the 2 handle protocol calls to get the device in the file system, opening the volume to get the handle to the file system, and then the standard stuff to open files, allocating memory. All right, so now the fun part is to understand the UEFI file parsers you can actually involve. So how does it execute binaries? All right, so there's 2 file formats that are used that you can use in UEFI. There's the portable executable, which is just the regular 64-bit exe. There's also the toast executable, which is a stripped down version of the PE. I didn't play with this one because I didn't really know where to start with it, and I already knew a bunch about portable executable, so I didn't want to go too further with it, but there's 2 file formats supported. And when you do run an application in the shell, calls the load image function, which is basically a series of calls to a few other things. Starts off at food services, which is like the running thing that actually gets your input. Calls load image and then goes down a series of things till it gets to a function called PE cof loader get PE header, which is what we care about to get our super tiny file loaded into memory. So it's actually not a lot of checks. It's actually way less checks than Windows, but there are a few things that it needs to have in order to even load your file into memory in the first place. So you need to have the number of RVA sizes needs to be correct. The optional header size also needs to be correct. You have the exact number of sections. There's the size of headers has to be the correct number. It's basically a bunch of standing checks. This one was tricky though. The image data, directory entries, they need to contain Yeah, EFI image, well, this is the data directory for security, just the sixth one. So it does check that, even though you can not use it, it still has to be present in the file to get past the loader. So that results in the minimum viable PE for UEFI, which is just the MZ header, PE header, optional header, all those data directories, which can all be blank. You'll see a section head before the text section, and then your code. So kind of a lot of things you need to have, but we can start with them. So, start about golf. All right, so golf is trying to go out of free on the so since we're using a PE and understand how the parser works now, we can use a lot of the content techniques to make a small PE, which is really useful. So if you're using OBMF and QEMU, you can also rely on some of those quirks of how we know that works too, to make the binaries. Downside though is targeting OBMF makes it not portable to other systems as much. You've heard of different quirks, but I'm looking for a small spine. So if anybody doesn't know about tiny PE, it's basically this technique for making the binary super small by shrinking the header. The way it works is a DOS field in DOS header called UEFI, and if you set that to 0x4, it'll start parsing the PE header as 0x4 in DOS, in the whole file itself. So you can overlay and save a bunch of space by overlaying two things, because we don't really care too much about what happens in the DOS header. It's basically just a pointer to the PE header, so you can overlay a bunch of stuff on it and limit for you. Also, the minimum size for a 64-bit portable CPU is 238 bytes, and it does family check on all the things that I was talking about before, and it's 238 bytes. And this is the same limit, lower limit on 64-bit Windows as well. Yeah, so actually test this was pretty annoying because OBMF, when you start it, there's a 5-second delay that is a countdown, which you can interrupt by pressing the delete key, but you have to do that every time you want to test something. So it's incredibly slow. So what I ended up doing was making a script, just run QEMU and set up all this stuff and just put all the inputs in for me. It's a task screening kind of thing of the OBMF interface. And also, I did the thing too for the script as well. So basically, I have it in the repo, which I was going to mention at the end of this, but there's a script basically doing the building for all this and give me a map so I can take all these things and map them to breakpoints. So I can very easily just have a script to be a debugging helper. And also, a really cool thing I found out in this was that if you put map all and then like my.bit.map at the top of your NASM source, it creates this map file which has all these breakpoints for students. It's really cool. I didn't know about that. All right, so we have a small file of the PE header, got a little bit of code to test with. So the thing I have to do next is explore the caves inside of the header where you can store data, because the goal is going to be to put as much data as we can in the header so that we don't have it in the other files. Because we already know the size of the header is going to be constant and it's going to be the same size regardless. But the code section, if we can shrink that as much as possible, then that's the goal of the whole challenge. So I ended up doing this with manual testing to just write the word free and all the different faces at the top there, and as long as it was still executed, then it was fine. Big shout out to my friend Ombre for talking me out of writing a snapshot fuzzer that I was going to for QEMU, but it was going to be way too over-engineered for this challenge. But yeah, this is what it looks like when I was testing. So I had to confirm that the header was actually loaded properly too, because sometimes platforms will map the binary to a different location based on virtual addresses that are defined in the header. And so you have to make sure that everything is loaded in memory at the same relative offsets together so that you can jump back into the header and vice versa. And so to do that, you have to just adjust the address of entry point in the PE header and put it right at the end of where the header actually ends, instead of putting it somewhere else virtually. I also had to confirm that the header wasn't modified or anything weird happened to it, so I dumped it from Jesus. And so the next step to this is going to be, now that we know where we can go in the header, until you figure out how to jump around it. So, to do this, you need to know the exact size of the instructions on a binary level. So I used NDisASM, which is the disassembler counterpart of NASM, just giving straight disassembly and everything. But I started to do that took all the bytes, and I basically divided up the code into like little chunks of around 8 to 12 bytes of a basic block, like a slightly basic block. And so Phil will know about short jumping inside of x86. Short jump is 2 bytes. You can only jump backwards and forwards of limited range. The 125 bytes backwards because it has to jump over the 2 byte instruction. So you only have 125 bytes backwards, 127 forwards. If you do go any further than that, the instruction that gets assembled is going to be a larger instruction, which we don't have. And this is a really thick website. It's very 90s, Starman's realm. As it's short jump tables, I think some of the references, one of my favorites. So, all right, now we're going to store our data and code in the header. So we have the free spaces, we know what they are, we know what we need to, what we can't overwrite. And so every space that you put code into that you're going to jump around in, you need to make sure that you account for the 2 bytes for your short jump. So that's another constraint we have to remember. And also, if you're doing data references to the relative offset, it has to be pretty close to where you're at in the code itself or in the binary. So that keeps everything really small. You can just kind of not have like a row data section or something like that. Another strategy that I had for this was to assume the address to 32-bit because 64-bit registers and instructions are going to be a lot larger because they have to account for all the zeros that you're going to need. So OBMS seems to only use 32-bit addresses. Maybe it's in other platforms, but targeting OBMF itself, I knew that it was going to do this, so I could do like move EAX, EAX rather than move something to EAX instead of RAX, and it would save me 4 bytes or more per instruction. And also, same as well as using only the base registers of RX to RDX, because using any data registers of I9 with that will be larger because they're encoded. They're added on out, so the encoding is a bit bigger, even if you're using slices of registers, like basically large through R15. So another thing that I could do too was reuse register values, which is really cool because we're in GDP, so obviously it doesn't count if your thing works in GDP, but we're able to at least know some of the values that are in the registers after calls will be consistent as long as the call continued to work. So being able to reuse the values was really cool because it saved a lot of space. If you usually have 2 or something, you can get it from a reliable source. So doing a register to register move is a lot better, or a lot smaller than like a stack reference or some other data reference. And so also the big thing I did was assuming that RAS is going to be 0 after a call because that indicates EFI success. And so doing that gives you like basically a free 0. As long as the call works, which is like I made this assumption early on, which is kind of why my stuff broke early on too, but it happens. All right. So another strategy is just shrink your constants with code as much as possible. I told you about the GUIDs and things like that, which are very long, can't really do much with them. You could try to execute this code, but it's kind of a lot. So there were other constants that I had to kind of work with to try to turn them into something. So I did that in a few other portions of the code here too. But so a big piece of this though, which is familiar to people who are code golfers, is Kolmogorov complexity, which is just the complexity of computing a string, right? Like if there's representing an AB a bunch versus this other string, and you can just do like 80 times 16 or something and get the same result, but it's larger to calculate them. So that's a big part of this. And thinking about binary golf itself, is just how do you shrink certain things and what things aren't worth trying to shrink. Because sometimes optimizations can be bigger than the regular version of the code. The final one that I had here was just crowdsourcing. So I had this little puzzle that I put out on Twitter that I was like, maybe somebody will give you a better answer. But I found this thing which I was talking about with the larger registers here, moving this big value into R9. This is actually the file attributes that I was talking about. But some of the tricks that I had, like doing rotates and other bit shift stuff, was not something that was easy to do with the register that I was acting on. So there's a few examples in here. I have like move absolute R9 this value, but then like lowering R9, adding 7, doing a rotate right, for doing other rotations. Just like there was a bunch of different tricks I tried, all of them were the exact same size as the original instruction. So I was like pulling my hair out, and I had a couple of ideas of how to do it, but I was trying to figure out if anybody could do it smaller. And so I ended up getting loop optimization, which was just a push setting, pop it into R9, and then just work it right, which shifted the 7 to put that top bit at 8, and then we have this whole value here. So this doesn't work on a lot of different other platforms, so your mileage will be very chips like this, but it worked in this specific case, so I was happy. Yeah, it's definitely a valid strategy. Another strategy I had was just to not clean up after myself, so I didn't free stuff after I was done with the into. I didn't close the original file. Basically, I just had it to the only behaviors I actually need to do. I got this down to 440 bytes, which is already sick, because I cut and passed the last entry to BGGP, because there was 2 other UEFI apps that I got down to 440. I was like, I wonder how far I can go. Basically, 238 is the bottom limit, so there's only so much further I can actually do it, but the last trick that I had that I really wanted to share was that one of the PE headers values of the subsystem, which says that which subsystem for Windows usually, but for whatever platform you're on, you're using. So A is the console, and so the subsystem value needed to be this, and it separated 2 of the 3 zones. But I had 2 actually large free zones, and so it was really frustrating. I'm like, what do I do with this? Like, I have to account for this and jump around in things. And so I basically looked for anything in my code that had a 000A, and I found that because we're using UTF-16 strings, so I could take the 0 that's after the 3-4 in there, and the new line, and use that as a subsystem value. So I lined up everything inside of the binary, and then was able to clear out a bunch of the other space and use it fully. So once I got this to 420 bytes, I thought it was done, because 420 is the gamer number. So yeah, and the final result here is a 420 byte UEFI app that self-replicates here. This is the test script where it builds it, and then you see it running inside. There's 420 bytes for the QEMU. I have the HMP QEMU commands to instrument it, and then you see the running the file called A, it prints 4, and then comparing A to 4, and there's no difference counter with the shell, and you have the self-rep. Yeah. So there are some things you can do still. If you do want to play with this code, it's on GitHub, so you can absolutely play with it. But I was happy with the result that I had so far. I had already been working on it for so long. I was like so far removed. This was going to be a boot camp like 2 years ago, and then it turned into this. So, but there's a bunch of things you can do. You can play with some of the stack purposes and things, seeing the coefficients. But I was happy with working. So, and so I have this final piece, which is a more practical example, which is kind of run through. But BGGP 5 is happening right now, and it's happening until September. And so I had a really cool demo that I was going to do, but I didn't want to spoil it because I'm going to just re-implement everything for BGGP 5. So if you're interested, go to binary.golf/5, and you can check out the crazy ass page that we have. This is the flyer for it. So I'm really encouraging all of you to play it if you want to, because it's a lot of fun. There's a lot of weird tricks that you can do, and I'm excited to demonstrate basically a fancy little hook. And so that's pretty much it. You keep in touch. My website is nsbear.lol. We have binary.golf. We have Twitter, and we have this BGGP Recon. We also have a Discord with some cool people talking and stuff. And I think that's pretty much it. Yeah, just a lot of other references. So that's it. Yeah. Okay. Now we're going to come up with this pretty fast, so basically we can party early. And do we have any questions? Use that.
Hey, we have a mic.
Yeah, you did.
Yeah, so you did a lot of things like not cleaning up after your registers, and assuming the registers get zeroed out after
a period of time, which could work on some systems and could work on other systems. So I'm kind of trying to, because I'm curious, it's a cool exercise. I'm curious what are the metrics for the parameters for these tasks. Does it have to run on a system, or does it have to run on a series?
As long as it can be verified by another person, that's it. It's pretty much the only criteria. So if you give a challenge that's like, we're running on this specific thing with environment variables or stuff, or whatever, as long as we can replicate that in our lab, any of the other verifiers, then that's pretty much the only criteria for it. Because we know that like people are going to do tricks that might be platform specific or platform they're really familiar with. So we want to see those tricks, but we also want to make sure that other people can actually replicate it. So it can't just be like a chance, like a thing, that crazy machine or something. It has to be something we can replicate in our lab.
Okay, thanks.
I have a wait for that mobile hands running very fast.
I'm not super familiar with binary golfing and the whole amount of research that may surround it, but have you or others, or at least are you familiar with people using potentially jumps to midpoints in instructions and variable length architectures like x86 to for golfing?
So if you look at it, there's actually several examples of that inside of our repo. And the first one, I actually do that in my ELF. I did an ELF palindrome, and I jump into the window of instructions. You can also do like a short jump backwards, like at an uneven time, and then execute the short jump itself as piece of code elsewhere. So there's a lot of tricks that you can do with that, and there are cool demonstrations. So if you, basically everything's on GitHub, so you can see all the code for it. So I would take a look at that, because there's stuff like that too. You can't really do it on things like Honor. Maybe you can, if you're really tricky. But
For instance, something with like, maybe with something like an instruction that executes under both normal mode and thumb mode or something.
Yeah, there are things that I haven't seen that in BGGP itself yet, but I know that it's possible. It's just great. Yeah. Definitely check out the repo though.
Thank you.
Which is that's one. Sorry. Any more questions? Oh, you.
Have you considered the UEFI bytecode instead of
The UEFI bytecode?
Yeah.
So Nika actually basically did a talk at Defcon about targeting UEFI bytecode, because I didn't even know about it. She was like, "Oh, I'm gonna write the next one for UEFI bytecode." Never heard of it. So it is something you can do. I didn't do anything with it, but she did the Defcon talk about it. And I think maybe even things that the talk is doing tomorrow. So if you're curious about how that VM works, it's really cool. But I think you're really good at it. Thank you. Anyone? Cool. All right. Thank you all so much. See you all. Yeah.